So in this part, let us talk about something a little different from uniqueness. So essentially this is a uniqueness, but this is called a backward uniqueness. Okay, so backward uniqueness. Now you see in Laplacian what happens is you just have a omega, and in that domain you are just working out if the solution is unique or not. But here there is a time variable which is involved, right? So a natural question is this: see, initially in uniqueness what we did is we just assumed that u is g on some parabolic boundary and it satisfies the inhomogeneous equation. You have to show that the solution is unique or not, and we have seen that the solution is unique. But if the question is something like this, let's say if the question is let's say let u and u tilde, okay, this satisfies ut minus Laplacian of u equals to 0 in omega t, and u equals to g on the only the del omega cross 0 t. So del omega cross 0 t, okay, so only the sides, if you will. So let's say that's your domain, okay, let's say this is our domain. Boundary of omega is this, right, del omega. So let's say that's your omega, yeah, and this cross 0 t, so only this part, okay, so only the top part, this part, only this part, nothing inside, not inside, nothing inside, only this part, that part, this part and this part, right? So a point here, does it belongs to that set? No. So the boundary, we are only looking at the parabolic boundary minus the base, this base, okay. Of course the boundary is included, okay, the boundary of omega cross t equals to 0 is included, so that is there, okay. So let's say u satisfies this equation and u tilde also satisfies this equation. So ut tilde minus Laplacian of u, this is 0 in omega t, okay, and u tilde, okay, is g on the boundary cross 0 t. Sorry, okay. So this is for some g continuous, clear? Now one small remark here, so what am I starting out with? I am starting out with two functions u and u tilde, such that u satisfies this equation and u tilde satisfies this equation. So essentially they satisfies both the same equation, yeah. But you note that we are not assuming u and u tilde, okay, are equal at time t equals to 0, okay. So we are not assuming they are equal. You see, it may be different, right? And these points we don't know. We just know that on the boundary u is g and u tilde is g, that's all, yeah. On the boundary they are equal, yeah, of course, on this boundary, not at these points, huh? So t equals to 0, it may or may not be equal, so we are not assuming they are equal, okay. Now what is backward uniqueness says? The theorem says, okay, let u and u tilde is in C21 omega t, okay, bar, of course, bar. So we are always taking the boundary and solves 1 and 2. What is 1? This is 1 and that's your 2, okay. So let's say this solves 1 and 2, yeah. And if this is very important, u at x t equals to u tilde at x and capital T, okay, and x is in omega. So what does it say? It says that u and u tilde, they are same for, let's say this is some t, okay. I mean, see, here I am just putting this t here, there is nothing special about this t, okay. It can be here also, it can be here also. So let's say t for now, let's just assume that this is t. I mean, the cylinder may go on, yeah, it's not like specified up till here only it can be. So omega t can be here also. So let's say t1. So I can do it for omega t1 also. Okay. So if that happens, then so essentially, if for any time t, yeah, for let's say t equals to t1 or t equals to t, so small t equals to capital T or small t equals to capital T1, whatever it is, yeah, if that is happening, if u is same for all x capital T and u and u tilde are same essentially at those points, okay, then what happens is you can say u is equivalent to u tilde in omega capital T, okay. So what this is saying is, let's put it another small remark. It is saying that if the two distributions, okay, on omega, if the two distributions means functions maybe, okay, functions u and u tilde, okay, let's say they of course in omega agrees, okay, at some time t, okay, of course this is positive, so let's say t1 positive, then, and of course the boundary values, so you see the boundary values has to be same, okay, and then they are equal provided they share a common boundary, values, okay, values for all time 0 t t1, okay. So essentially I am taking t1 here, you can just say t1 to be capital T, that's not a point, that's not a problem, okay. So here what it is saying is, if it is same at some point, see this is important, at some point, okay, if it is same at some point, then it is saying that they are equal, of course the boundary condition has to be equal for all t, and then so this is capital, okay, let's put it like this is t less than t1, okay. So if this is if this is this holds for all t between 0 and t1, then the functions are identically equal. So you have to have the function equal for some t, okay, for some t, and then on the boundary it has to be equal for all those t, for all t below this capital T1, then the functions are same, okay. So let's look at the proof of this thing. So what is the proof of this thing? First, of course, we are starting out with our usual things. So we define W, which is u minus u tilde, okay, and of course this is in omega t, and once you define this thing, then and set, this is our usual thing, whatever we did earlier, omega square xt dx, okay. So essentially I am taking I'm fixing a t, and for each fixed t I am defining a et such that this is the square of w, and this is holds for all t between 0 and capital T, yeah, okay. If that happens, then of course you can you see w is u minus u tilde is twice continuously differentiable, right, with respect to x, and once continuously differentiable with respect to t. So essentially this is thrice differentiable, this function e of t. So I can take at least one different derivative here. If I take one derivative here, that will give you 2 integral over omega. If you remember, this is omega of xt, omega t of xt, right? Why can I write it like this? Because you see I can take the derivative with respect to t inside, because this is the integral with respect to x. Now if I just replace, you see wt satisfies what? Wt satisfies 0. Wt equals to Laplacian w in omega, right? So essentially this is equals to integral over omega w of xt and Laplacian of w xt dt, right? That's what you are going to get. And after that, integration by parts, since wt equals to Laplacian of w, right? And see, after you do a integration by parts, that will give you minus 2 times integral over omega gradient of w square dx. I hope this is fine. I mean, we did this earlier also, okay? Right. Of course, this prime, I mean, the prime is ddt with respect to time. Fine. Now, what we are going to do is we are going to take the another derivative. As I told you, et is thrice differentiable, so I can talk about the e double prime of t. What is e double prime of t? If you can just I mean, there is nothing to do here, so let me just write it down. It is gradient of wt d of x, right? Why? Because you see, essentially you have gradient of w dot gradient of w, right? I mean, if you take the derivative of this thing, so it is basically gradient of wt plus gradient of wt gradient of w, okay? And then you will get this thing. See, here this gradient is with respect to x, okay? That is why with respect to t this is going inside, okay? So you have this, and again gradient of wt is Laplacian of w, so this will give you 4 integral over omega Laplacian of w. Where is it? Yeah, one sec. Laplacian, okay, sorry, wt, right? Wt we can't change. We know what Laplacian of w is, or do we? What do we know? We know that oh, okay. So no, I won't change it here. I will do an integration by parts here. Okay, I will do an integration by parts, and I will push this in derivative here. So it is integral over w. It will become I mean, Laplacian of w dot wt, okay, d of x. Is this clear? And what about the boundary condition? See, w is 0 on the boundary, okay, on del omega. So that's not there. Clear? Because u is u tilde on del omega, right? So this is true, okay? So now what we want to do is this. See, Laplacian of wt is Laplacian of w. So this essentially says this is 4 integral Laplacian of w square d of x, right? This is what we are going to get, e double prime of t. Now therefore, what do we get? See, therefore integral over omega gradient of w square d of x, yes, this is equals to, let's say, integral, this is what we got last time, it is w Laplacian of w d of x, right? Gradient of w squared, if we just write it from integration by parts, we are going to get this because w is 0 on the boundary, right? So we are going to get this. Now once you get this, you can take the mod of this thing, the absolute value of this thing is less than equal, I am not writing all that, is less than equals to integral over omega w square whole power half and integral over omega Laplacian of w square dx, let's write dx whole power half. Yes, this is true. See, minus of this thing, if you take the modulus of this, that will be less than equal integral over omega mod of this thing, and then you use Cauchy-Schwarz inequality to get what we just wrote. This is Cauchy-Schwarz. Clear? It's Cauchy-Schwarz inequality. Now once we do this thing, then what do we have? Then e prime of t, let's take the square of this thing, okay, e prime of t square, that is what? It is 4 integral over omega gradient of w square dx whole square. Clear? Okay, and that is equals to less than equals to integral over omega w square dx and integral over omega 4, I will write it like this, Laplacian of w square dx. Clear? And this is what? This is e of t, e double prime of t. I hope this is clear to you. See, gradient of w square dx is this, right? So I just wrote it here, and after that put the 4 inside. If I am putting the 4 inside, that is what? This is essentially e double prime of t. So that is e double prime of t. So maybe I can write it like this. It will be more clear. Let me put it this way. So e double prime of t. Clear? Okay. So what do we have? We have that therefore we have that e double prime of t times e of t, this is greater than equal e prime of t square. okay, for all 0 less than t less than capital T. Now this inequality, if you look at properly, see, this is minus e prime t square is greater than 0, right? And that will give you some, I mean, something like e of t by e prime of t, the derivative, sorry, e prime of t by e t, the derivative of that, right? Something like that. I mean, if you just write it together, this is an ODE. So essentially this gives us an idea what is that idea. So let me write it. So basically there is some log involved here. Yeah, if I involve a log here, I will tell you what all of this means. So for the next step, what we do is, now see, if e of t, I want to show uniqueness, right? So if e of t is identically equals to 0 for all t between 0 and capital T, then we are done. Right? Why we are done? Because e of t is integral of w square. If e of t is identically equals to 0, the integral of w squared is 0, that will give you w is 0, and that will give you e equals to u tilde. So we are done. Otherwise, okay, let's say there exists an interval t1 and t2, which is containing, of course, 0 capital T, such that, okay, e of t is greater than 0, okay, for t1 less than t less than t2, and e of t2 is 0. This is always true. Yes, if it is not 0, if it is positive somewhere, then this kind of thing is bound to happen. Why there is always a t2 such that e of t2 is 0? Because e of t is always e of capital T. If you just look at what is e of capital T, okay, so you see, this is for any t2 between 0 and t, and what is e of capital T? E of capital T is going to be 0, right? E of capital T is 0. So essentially what is happening is, there is always such a t for which all of this happens. Okay, so now what you do is, now, okay, we write g of t, you define g of t to be log of et. Okay, and once you define it, you can actually show that g prime of t, this I want you guys to do yourself. This is very easy. This is always greater than equal to 0. How? Let's say that is star from star. I hope this is quite fine. See, what is g prime t? It is e prime of t by et, right? And after the g prime t is essentially, g double prime t is essentially this thing, and this is greater than equal to 0, therefore g double prime t is greater than equal to 0. Okay, so what does that give you? Therefore that says that g is convex in t1 t2, right? It says that it is convex in, sorry, it is open t1 t2. It has to be open t1 t2. It is in open t1 and t2. Okay, that is what it is saying. So now once it is convex in open t1 t2, what we can do is, we can just write it like, you see, for 0 less than tau less than 1, okay, and t1 less than t less than t2, we have g of 1 minus tau t1 plus tau t. Okay, this is less than equal 1 minus tau f of t1 plus tau f of t. Right, I can write it like this. So for any t between t1 and t2, I can just write the expression like this. Okay, and see, if what is g? G is log of exponential t. So if I just put it together, what is going to happen? Log of, sorry, not exponential, sorry, g of t is log of et, right? See, g of t is log of et. Right, if you put it together, what is going to happen? This will just be exponential, sorry, it's not exponential, yeah, it is 1 minus tau times t1 plus tau t. This is less than equals to, log is there, so this will go inside, e of t1 1 minus tau e of t to the power tau. Okay, this is for 0 tau 1. Clear? And if this is happening by continuity, what can you say? By continuity, once you use continuity and take t towards t2 minus, okay, by continuity, when t goes to t2 minus, what happens? This will convert to, see, e is a continuous function, okay, so this will convert, so e power tau is also continuous for tau between 0 and 1, and hence this will convert to e power t2. Yeah, this holds for all t between, so this will convert to e power t2. So again, exponent the function e is always positive function, right? This is always positive function because e of t, yeah, for all t, so this is positive, right? So essentially what is happening is 0 less than equal, so non-negative, sorry, exponential is always sorry, not exponential, what am I saying? E of t, see, e of t is integral of w square, right? So it is a integral of a square function, so it is never negative, so it is always non-negative, right? So this is 0 less than equals to exponential 1 minus tau t1 plus tau t less than equal exponential t2 1 minus t1 1 minus tau exponential t to the power tau. Now when this thing goes, t goes to t2, this will go to exponential t2 to the power tau, okay, exponential t1 1 minus tau, this is less than equals to this, less than equals to 0, okay. So what does that mean? It means that therefore it means that exponential t is 0 because exponential, sorry, no, what am I saying? Why am I saying exponential? This is e, yeah, I am really sorry about this, yeah. So this is e, yes, not exponential. So e power t, this is 0 for t1 t2, yeah, this is 0. See, this is given to be 0. This is what our assumption was. This is 0, and so whatever is inside, you know, e for all this t which looks like this. So the line segment containing t and t1, t1 and t2, for all those t, e of t is 0 because this is 0, this is 0. So this is sandwiched between 0. So this e power, this e of this, all these points are 0. So that is going to be 0. This is a contradiction. That's a contradiction to the fact that e power t is positive. That is what we assumed, okay, and hence it is proved that therefore e power t has to be identically equals to 0. That is, u should always be u delta. Clear? Within omega t. Okay, one small thing I want to again explain. I'm really very sorry, these are not exponentials. Yeah, I don't know why I am just calling it exponential, because you know, whenever we see e, we just write it as exponential, but this is not an exponential, this is the function e. Okay, this is some function e, so I'm really sorry about that. Okay, so with this we are going to end this particular topic, and next topic we are going to start with fundamental solution.